5 hours and 12 minutes. That is the gap between two major volcanic eruptions on the same continent, on the same ring of fire, inside the same geological era, but in two different countries, driven by two different tectonic plates, through two different magma systems that have no known mechanical connection to each other, two geological events that by every standard model of volcanic behavior had no reason to happen within the same narrow window of time. That number was sitting on the desks of scientists at the Philippine Institute of Volcanology and Seismology in Manila, and scientists at Indonesia's Center for Volcanology and Geological Hazard Mitigation in Bandung before the sun had risen on either city. They had been awake through the night, watching their instruments, issuing alerts, coordinating evacuations, and trying to answer the question that 5 hours and 12 minutes had placed in front of them, whether two geological events that should have been independent had just demonstrated that they were not. They do not yet have the answer. The instruments are still running. The eruptions are still ongoing. The science is watching in real time. And by the time this video is over, you will understand exactly what that gap is asking, and why the answer to its question matters for millions of people who are not in any evacuation zone and have not yet been told to pay attention. At 3:47 in the morning Philippine Standard Time, Taal volcano woke up. Taal sits within a caldera lake in Batangas province, approximately 70 kilometers south of Metro Manila, in one of the most unusual volcanic configurations on Earth. A volcano on an island inside a lake inside a caldera, layers of geological history stacked on top of each other in a structure that has been building and collapsing and rebuilding for hundreds of thousands of years. The eruption that began in those pre-dawn hours was not the slow emergence of lava down a mountainside. It was a collision between two incompatible physical states, magma, at roughly 1,100 degrees Celsius, meeting the 267 square kilometers of lake water sitting directly above the volcanic vent. When that collision happens, the word eruption barely covers it. Water at ambient lake temperature contacting rock at magmatic temperature does not boil in any conventional sense, and the transition from liquid to steam is so instantaneous and so energetic, the water expands to approximately 1,700 times its original volume in milliseconds, that the process functions less like a phase change and more like a detonation. The expanding steam shatters the magma into fine glass particles. It drives those particles upward. Within 90 minutes of the eruption's onset, the column of ash, gas, and fragmented rock had risen 15 kilometers above sea level. 15 kilometers is not just a large number, it is a threshold. The troposphere, the lower atmosphere, where weather happens, where rain falls, where particles eventually wash back to the surface, reaches to approximately 12 to 15 kilometers altitude at equatorial latitudes. Taal's eruption column crossed that threshold. The material injected above 15 kilometers entered the stratosphere, the cold, stable, nearly precipitation-free layer above the weather. Particles that reach the stratosphere do not fall out in days. They circle the globe for months to years. The sulfur dioxide reaching stratospheric altitude was already, before the sun rose, being tracked by atmospheric chemistry teams who began running models on its potential regional and global impact before either Manila or Yogyakarta had issued their morning weather reports. The Philippine Institute of Volcanology and Seismology raised the alert level to level 4. Hazardous eruption occurring. Mandatory evacuation orders went out for a 14-kilometer radius around the volcano, and sulfur dioxide emissions registered at an estimated 8,400 tons per day, more than 3 times the background rate of the preceding weeks, a spike large enough to place this eruption in the category of events that atmospheric scientists take seriously at a global level, not merely a regional one. 5 hours and 12 minutes after Taal's column pierced the cloud layer above Batangas province, something happened 3,200 kilometers to the southwest that the monitoring teams at PVMBG had been watching for but had not predicted on this timeline. Mount Merope's summit dome collapsed. Merope is not a lake floor volcano. It is a classic andesitic stratovolcano, the archetypal shape of a volcano as most people visualize it, a steep symmetrical cone rising above the rice terraces and forests of central Java, sitting approximately 28 kilometers north of Yogyakarta. The city has lived with Merope for centuries. The mountain is woven into Javanese culture and spirituality in ways that coexist, uneasily but durably, with the knowledge that it is one of the most dangerous volcanoes on Earth. For the past several months, Merope had been doing what it does between major eruptions, building a lava dome in its summit crater, slowly extruding new rock, growing incrementally toward a point of instability. That point arrived in the early hours of the same day that Taal erupted. The dome collapse sent pyroclastic density currents, flows of superheated gas, ash, and rock fragments, down the mountain's southern and southwestern flanks. These flows moved at speeds estimated between 100 and 300 kilometers per hour, carrying material at temperatures exceeding 700 degrees Celsius. They travelled 7 kilometers from the summit before their momentum was exhausted. The eruption column that rose above the collapse reached 12 kilometers. Indonesia's alert system elevated Merope to level 4 AWAS. Danger, the highest designation in the system, the designation that means the volcano is in an active state of major eruption with potential for further escalation. Aviation authorities across Southeast Asia issued volcanic ash advisories within hours of the second eruption. Both Manila's Ninoy Aquino International Airport and Yogyakarta's Adi Sucipto Airport suspended all operations. The VAAC Darwin and VAAC Tokyo, the Volcanic Ash Advisory Centers responsible for coordinating aviation warnings across different sections of the region, issued emergency advisories covering flight corridors between Europe, the Middle East, and Australia. The routes that connect the world's largest aviation market regions were now threading through airspace contaminated by two separate ash plumes, expanding from two separate volcanic systems across overlapping trajectories. The news coverage of that morning ran both stories: major eruptions in Asia, dramatic footage, significant evacuations, important, both true, and nearly every major outlet ran them as adjacent columns, separate stories about separate events that happened to land on the same news day. Two headlines sharing a page by coincidence. The headline framing is not wrong. The geological consensus holds that Taal and Merope have no direct mechanical connection. They sit on different subsystems of the Western Pacific convergent margin. Their magma is generated by the subduction of two different tectonic plates. Their eruptive histories are independent. The mainstream scientific position is that two volcanoes on the same broad arc can and do enter eruptive phases independently, and the 5-hour and 12-minute gap is an unlikely coincidence, but a coincidence nonetheless. But there is data from the 60 days before both eruptions that complicates the coincidence framing in ways that the volcanic science community is now actively examining. There is a piece of the story embedded in the architecture of global aviation safety that represents a real, there's immediate danger not captured in any of the morning's news coverage. And there is a pattern in the historical record of the Western Pacific Arc that, once you know it, makes the question embedded in 5 hours and 12 minutes harder to simply set aside. The story here is not two volcanoes. It is everything those two volcanoes are sitting inside. To understand what is actually happening, you have to go to the floor of the ocean, approximately 200 kilometers east of the Philippine Islands, where an oceanic tectonic plate is descending into the Earth's mantle at a rate of about 7 centimeters per year. The Philippine Sea Plate is one of the smaller tectonic plates on Earth, but it is among the most geologically consequential. It is oceanic crust, dense, dark basaltic rock, rich in iron and magnesium, heavy enough to sink when it meets the lighter, silica-rich material of the continental Eurasian plate at the convergent margin to the northwest. Where these two plates meet, the oceanic plate bends downward along a line marked at the surface by the Manila Trench, a deep, dark gash in the ocean floor where the seafloor folds and descends. From that trench, the Philippine Sea Plate travels downward into the mantle at an angle of roughly 45 to 60 degrees, getting hotter and denser as it goes, carrying everything it has accumulated over millions of years of existence as ocean floor. What it carries matters enormously. Oceanic crust is not just rock, it is hydrated rock. Over millions of years on the ocean floor, it has absorbed seawater into its mineral structure. Minerals like serpentine, chlorite, and amphibole hold water chemically bound within their crystal lattices. Water that cannot simply evaporate or drain away. Water that is locked into the physical structure of the rock itself. When the subducting plate reaches depths between roughly 80 and 150 kilometers below the surface, the increasing temperature and pressure trigger a process called metamorphic dehydration. The minerals break down under those conditions, releasing the water they have been holding. That water, now free, migrates upward through the fractured rock above, finding its way into the hot peridotite of the mantle wedge, the wedge-shaped volume of upper mantle caught between the descending oceanic plate below and the overlying continental crust above. This is where the first critical piece of chemistry occurs, and it is the chemistry that ultimately creates everything from Taal to Krakatoa to Fuji to Pinatubo. Water, in the context of mantle rock, is a flux, a chemical agent that depresses the melting point of the surrounding material. Rock that would stay solid at those depths and temperatures without water begins to melt when water is introduced. The melting does not require any additional heat. It requires only the presence of water, which unlocks a thermodynamic state change that would otherwise not occur. The resulting magma is not the same composition as magma generated at mid-ocean ridges or above hotspots. It is enriched in silica, carried from the subducting crust and the overlying continental material through which it rises. And silica content is the variable that determines whether a volcano builds lava flows or produces explosive eruptions. The more silica in the magma, the higher its viscosity, the more pressure it accumulates while rising, the more violently it decompresses when it finally reaches conditions of lower pressure near the surface. This is the engine that drives every volcano along the western Pacific Arc. Same deep process. Same fundamental chemistry of descending water and rising melt. But the surface expression of that process varies enormously depending on the specific geometry of the magma's path to the surface, the composition of the rock it travels through, and, in Taal's case, what is waiting for it at the vent. At Taal, what is waiting is a lake. The 267 square kilometers of Lake Taal sit directly above the volcanic vent system. The lake is the remnant of previous caldera-forming eruptions, the collapsed surface expression of a magma chamber that emptied catastrophically in past geological time and left a depression that eventually filled with water. The volcanic island that rises from the center of the lake, Volcano Island, is essentially the surface expression of the active vent poking up through 100 to 200 meters of water. When silica-rich magma rising through the conduit beneath that island contacts the lake water above it, the interaction is not a mixing or a gradual exchange of heat. It is the meeting of two physical states so thermally incompatible that the transition between them releases energy at a rate that the word boiling does not adequately convey. Imagine placing a teaspoon of water onto a steel plate heated to 1100 degrees Celsius. The water does not simply evaporate, it explodes. The Leidenfrost effect, the same phenomenon that makes water droplets skitter on a hot skillet, collapses completely at temperatures this extreme, and the water transitions directly into expanding steam with an energy release comparable to a small explosive charge. Now scale that to millions of cubic meters of lake water contacting magma at those temperatures simultaneously, and what you have is not an eruption in any conventional sense. What you have is a phreatomagmatic explosion, magma shattered into fine glass particles by the mechanical force of steam expansion, those particles driven upward at velocities that can exceed the speed of sound at the vent. The entire process powered not just by volcanic gases dissolved in the magma, but by the explosive thermodynamic energy of water becoming steam 1,000 times too fast. This is why Thal's ash column reached 15 kilometers in 90 minutes. This is why the particles it produced are extraordinarily fine. The mechanical violence of the phreatomagmatic process fragments magma more completely than a purely magmatic eruption would. And this is why the ash from Thal is, in some respects, more problematic than ash from a comparably sized purely magmatic eruption. Finer particles stay aloft longer, travel farther, and penetrate more deeply into respiratory systems. Merope operates by a different mechanism, though it shares the same subduction zone ancestry. The magma at Merope is andesitic, intermediate in silica content, viscous enough to be incapable of flowing freely down the slopes as a lava river, but not so silica-rich that it fragments explosively as it rises through the conduit. Instead, it rises slowly and extrudes into the summit crater, cooling and solidifying at the outer surface as it moves, building up a dome of progressively less plastic and more brittle rock above the active vent. The dome grows. Its outer surface hardens. The magma pushing up from below continues to inflate it. Month by month, the dome accumulates material and height until it reaches a point of failure. That failure, when it comes, is not subtle. Hundreds of thousands to millions of cubic meters of rock, some of it still hot enough to glow, while some of it partially solidified at the dome's surface, but still above 700 degrees Celsius internally, slides off the summit simultaneously. The motion of this material down the steep flanks of the volcano initiates a process that is neither a landslide nor an explosion, but has the most destructive properties of both. The rock gas and fine particle mixture forms a pyroclastic density current, a flow that behaves less like falling rock and more like a high-velocity fluid, following drainage channels and valley floors with a precision that makes it more dangerous, not less, than a simple avalanche that spreads diffusely across a slope. The physics of the pyroclastic density current's persistence are counterintuitive. You might expect the material to slow quickly as it spreads and cools. Instead, the density differential between the hot, particle-laden current, denser than the surrounding air because it is loaded with rock and ash, hotter because it is carrying its own thermal energy, creates a dynamic where the current is essentially buoyed from below by the expansion of its own heated gases while being contained from above by its own weight. This buoyancy maintenance mechanism keeps the current moving far longer and farther than momentum alone would predict. A current originating from a dome collapse at Merope's summit can maintain lethal velocities to distances of 7, 8, even 10 kilometers from the source. 7 kilometers. In the 2010 eruption of Merope, the flows reached 8 kilometers and killed 353 people despite the largest volcanic evacuation in Indonesian history. In the current eruption, the flows have reached 7 kilometers. The most proximal communities on the Kali Gendol drainage, communities that have lived under Merope's shadow for generations, communities that participate in regular evacuation drills, communities with a deep cultural and physical intimacy with the volcano above them are within that reach. That is what the mechanism actually means, not kilometers on a map. Specific villages, specific families, specific kilometers that determine whether the people who refuse to evacuate or could not evacuate in time have any time at all. The question of why both eruptions are happening now, within the same week, within the same 5-hour window, requires going one layer deeper than the mechanics of eruption. Every volcanic system has a cycle of activity and relative rest. Magma accumulates in the crust over years to decades, supplied by the ongoing process of dehydration and melting in the mantle below. The accumulating magma inflates the volcanic edifice, causing ground deformation measurable by GPS sensors and tilt meters. It fractures the surrounding rock as it forces its way toward the surface, generating earthquakes detectable by seismographs. Its dissolved gases, sulfur dioxide, carbon dioxide, hydrogen sulfide, separate from the magma as it rises into lower pressure environments and find their way to the surface through fracture networks, producing the elevated SO2 emissions that gas monitoring instruments track. These three signals, ground deformation, seismicity, SO2, are the primary toolkit of modern volcanic monitoring, and they are the signals that PHYVOLCS and PVMBG watch continuously at Taal and Merope, respectively. In the 2 weeks before both eruptions, both sets of monitoring networks registered the same pattern of accelerating precursors. At Taal, tiltmeter readings showing accelerating ground deformation, seismicity rates increasing above background, SO2 flux climbing to above normal. At Merope, GPS and tiltmeter data indicating renewed inflation of the dome and shallow conduit system, seismicity increasing with a character consistent with magma movement, SO2 flux rising. Both volcanoes were showing the precursor signatures of approaching eruption on roughly the same 14-day timeline before both erupted. Viewed individually, neither precursor sequence would surprise the monitoring teams. Both Taal and Merope are known active volcanoes with well-documented histories of exactly this kind of pre-eruption unrest, and both had been in continuous elevated monitoring states before this week. The current eruptions are, in that sense, expected, not in their precise timing, but in their eventual occurrence. The monitoring systems were built for exactly this. The part that does not fit the simple independent event framework is the parallel timeline, both volcanoes accelerating on roughly the same schedule, both crossing their respective eruption thresholds within 5 hours of each other. If both systems were approaching eruption through entirely independent processes, driven entirely by their own individual magma recharge rates and structural conditions, a coincidence like this is statistically possible. Possible, but unusual. The probability is low enough that the USGS flagged it for investigation. And then there is the matter of 47 days before the eruptions. 47 days before Taal and Merope erupted within 5 hours of each other, a magnitude 7.4 earthquake struck a portion of the Mariana Trench system approximately 1,400 kilometers east of the Philippines. It was a significant subduction earthquake, well within the range of events that occur regularly along the Western Pacific convergent margin. It produced a small tsunami warning that was later cancelled. It was reported in the news cycle and quickly forgotten. It generated no volcanic hazard alerts because the standard protocol does not call for volcanic hazard assessment following intermediate magnitude earthquakes at that distance. The standard model of how seismic energy propagates through the lithosphere predicts that dynamic stress changes from a magnitude 7.4 earthquake at 1,400 kilometers distance are too small, by the time they reach Tal or Merapi to materially affect the eruption timelines of those systems. This is the established consensus, supported by decades of volcanic monitoring data that generally shows no consistent relationship between earthquakes of this size at this distance and subsequent volcanic activity. But there is a body of evidence, smaller, contested, not establishing consensus but not negligible, that points toward a different possibility for volcanoes that are already near their eruption thresholds. Following the December 26, 2004 Indian Ocean earthquake, a magnitude 9.1 event, far larger than the Mariana Trench quake, volcanic monitoring teams across Southeast Asia recorded anomalous seismic activity at several volcanoes in the days to weeks following. Elevated tremor at Sumatran volcanic systems. Anomalous activity at Philippine arc volcanoes. The academic literature that followed produced papers on both sides, some showing statistical evidence of a post-earthquake volcanic response, others finding the data insufficient to establish a causal link. A mechanism was proposed to explain the minority findings. The dynamic passage of seismic waves from a large earthquake, even at great distance, could transiently perturb magmatic systems that were already close to their eruption thresholds. Systems already pressurized, already deforming, it was already generating elevated seismicity, essentially providing the final mechanical perturbation needed to push a primed system over the edge. The 2011 Tohoku earthquake, magnitude 9.0 off northeastern Japan, produced a similar subsequent debate. Anomalous volcanic responses at distant systems were documented in the weeks following the event. The academic discussion about seismic triggering of distant volcanic eruptions, a concept sometimes called dynamic triggering, is ongoing and unresolved. The Mariana Trench earthquake 47 days ago was a magnitude 7.4, not a magnitude 9. The dynamic stress changes it would have transmitted to Tal and Merapi at their respective distances are substantially smaller than those produced by the 2004 or 2011 events. The mainstream position would predict no meaningful volcanic response at those systems from an earthquake of this size at this distance. And yet the 14-day precursor acceleration at both Tal and Merapi, the ground deformation, the seismicity rate increase, the SO2 elevation, began roughly 4 to 6 weeks after that earthquake. That timeline falls within the range that the dynamic triggering hypothesis would predict for a delayed volcanic response. The seismic wave passes, the stress redistribution in the shallow crust propagates slowly, and systems already near their eruption thresholds begin to show accelerated precursor behavior in the weeks that follow. This is not proof. It is a timeline overlap that researchers are now documenting, because if it represents a real signal rather than coincidence, it has significant implications for how volcanic hazard is assessed in the weeks and months following major seismic events anywhere along the Ring of Fire. Every magnitude 7.4 or larger earthquake along the western Pacific Arc would need to be followed by enhanced monitoring of nearby volcanic systems for the subsequent 6 to 8 weeks. The monitoring infrastructure for that kind of response protocol does not currently exist at the scale it would require. The science on this is genuinely unsettled. What has happened in the past 24 hours is exactly the kind of event that either advances or conclusively fails to advance the dynamic triggering hypothesis, depending on what the detailed precursor analysis ultimately shows. Or scientists at PHIVOLCS and PVMBG are pulling their complete precursor records from the past 60 days and comparing them against the seismic timeline for the first time. That analysis will take months. Its conclusion will either reinforce the existing independent event model or require a revision of how the global volcanic science community thinks about seismic volcanic interaction in arc settings. The answer is not yet here. The question is now on the table. There is one element of this story that is receiving almost no attention in the news coverage, and it is the one that right now poses the most immediate risk to the largest number of people who are not in any evacuation zone and have not yet been told to pay particular attention. Southeast Asia is one of the most air-trafficked regions on Earth. The routes connecting Europe and the Middle East to Australia, New Zealand, and East Asia cross directly through the airspace that now contains volcanic ash plumes from two separate eruptions propagating across overlapping corridors simultaneously. These are among the most heavily used routes in commercial aviation. Hundreds of flights per day, dozens of carriers, hundreds of thousands of passengers. The economic and safety significance of these corridors is difficult to overstate. Volcanic ash is not smoke. It is not industrial particulate. It is not a temporary nuisance that clears when the eruption stops. Volcanic ash is glass. Specifically, it is composed of tiny shards of silicate glass, angular, sharp-edged particles with a Mohs hardness between 5 and 7, which places them harder than many of the metals used in the precision components of modern jet engines. When a commercial aircraft flies through volcanic ash at altitude, the particles enter the engines through the air intakes and travel into the compressor and turbine sections, where they encounter operating temperatures between 1,300 and 1,400 degrees Celsius. The melting point of volcanic glass ranges from roughly 700 to 1,100 degrees Celsius, depending on composition. At the temperatures inside a jet turbine, the ash particles melt completely. They become liquid glass moving through the turbine. As they travel into slightly cooler sections of the engine, turbine blades, fuel nozzles, turbine discs operating at lower temperatures, they re-solidify. They coat the surfaces with a layer of glass. That coating disrupts the aerodynamic profiles of turbine blades with tolerances measured in microns. It blocks the tiny cooling holes in modern turbine blades that prevent those blades from melting at operating temperatures. It alters the thermal balance of components engineered to operate within extraordinarily precise parameters. The result is progressive engine degradation that can, without warning and without any external indication visible to the crew, lead to complete engine flameout. On June 24, 1982, British Airways Flight 9, a Boeing 747-2, OO operated as the Speedbird Bravo. November service from Kuala Lumpur to Perth was flying at 37,000 feet over the Indian Ocean south of Java when it entered the ash cloud from Mount Galunggung in West Java. It was night. The ash was invisible in the darkness. The flight crew had no visual indication that anything was wrong. The first sign was a luminous glow around the engine nacelles, the St. Elmo's fire effect produced by ash particles ionizing as they struck the aircraft's surfaces. Within minutes, engine number 4 flamed out, then number 2, then number 1, then number 3. All 4 engines failed in sequence at cruise altitude over the open ocean. The aircraft descended without thrust from 37,000 feet, crew executing emergency restart procedures while the plane fell through an ash cloud they could not see and an ocean they were approaching. At approximately 12,000 feet, below the densest part of the ash layer, engine number 4 restarted. The remaining engines followed. The aircraft diverted to Jakarta. The windshield was so heavily sandblasted that the captain landed the aircraft almost entirely by instrument, looking through a small clear patch in the corner of the windscreen. All 247 passengers and 15 crew survived. The engines required complete turbine replacement before the aircraft could fly again. That was one volcano, one ash cloud at night, with no prior warning system and no VAAC in place. The aviation volcanic hazard monitoring system that exists today was built in significant part because of that event and the events that followed it. The current situation is more complex than anything the system was designed to handle. The Volcanic Ash Advisory Center Darwin is responsible for ash dispersal modeling from Merope. The Volcanic Ash Advisory Center Tokyo is responsible for ash dispersal modeling from TAL. These two centers are operated by different national meteorological agencies, the Australian Bureau of Meteorology and the Japan Meteorological Agency, respectively, under the coordination framework of the International Civil Aviation Organization. Each center runs its own atmospheric dispersion model for the volcano within its designated area of responsibility. Each center issues its own advisories to aviation authorities and airline operations centers within its region. What neither center does, what no system currently does, is run an integrated real-time combined plume model that accounts for the interaction, overlap, and compound contamination zone created by ash from two simultaneously erupting volcanoes in different responsibility regions. When the ash plume from Merope are propagating northeastward across the South China Sea and the Banda Sea, and the ash plume from Taal propagating westward toward the Bay of Bengal and southwestward toward Borneo, begin to occupy overlapping airspace between them, pilots and dispatchers routing flights through that region are working from two separate advisories that were each built for a single source scenario. The boundary between the VAAC Darwin and VAAC Tokyo regions of responsibility runs through exactly the airspace where the two plumes are now approaching each other. In the gap between the two advisory zones, the combined contamination picture is not fully modelled by either system. Airlines operating in that space are making routing decisions based on two separate advisories that were not designed to be combined and do not produce a unified picture of total risk. This architectural gap was identified after the last comparable event. In September and October 1994, when Rabaul caldera in Papua New Guinea and Merope in Indonesia both entered major eruptive phases within days of each other, the same problem emerged. Two ash plumes from two active volcanoes propagating through overlapping airspace without a unified tracking system. The International Civil Aviation Organization's Volcanic Ash Task Force discussed the need for multi-source ash modeling capability at its meetings in the years following. Those discussions identified the gap. They did not close it. That was 32 years ago. The gap is still open. It is open right now, in the airspace above one of the world's busiest intercontinental aviation corridors, while two volcanoes simultaneously generate ash plumes that the global aviation safety system was not built to track as a combined event. The pilots flying through that airspace tonight do not know this. Their dispatchers know there are two advisories and are doing their best to integrate them. The system they are working within is doing what it was built to do, but it was built for a different scenario than the one it is currently managing. To understand the full scope of what is happening, you have to look at the 60-day window before both eruptions, not just at the eruptions themselves, but at the state of the geological system that produced them. 47 days before Taal and Merope erupted within 5 hours of each other, the magnitude 7.4 Mariana Trench earthquake. In the weeks following that earthquake, seismological networks across the Western Pacific registered elevated microseismic activity along the Philippine sea plate margin. Not a single dramatic event, but an increase in the density of small events below the threshold of public notice. This kind of diffuse low-level seismicity after a major earthquake is a known phenomenon. The main shock redistributes stress across the surrounding plate, and the stress redistribution works its way through the crust as a cascade of smaller adjustments over weeks to months. In the 3 weeks before the dual eruptions, Mayon Volcano on the island of Luzon in the Philippines, approximately 400 kilometers southeast of Taal, reached alert level 2. Its SO2 emissions had been rising. Rockfall activity from the summit had increased, a precursor consistent with fresh magma intruding into the shallow conduit and destabilizing existing material. Mayon is one of the most historically active volcanoes in the Philippines, with more than 50 recorded eruptions. It has erupted explosively with significant pyroclastic flows and lava flows within the past decade. It is not currently in crisis, but it is not at rest. On the island of Negros, in the Philippine Visayas, Canlaon volcano had reached alert level 2 3 weeks before the dual eruptions following a series of phreatic explosions. Steam-driven blasts not involving fresh magma, but indicating elevated hydrothermal activity within the volcanic system. In phreatic explosions at Canlaon are driven by groundwater contacting hot rock in the shallow volcanic edifice, the same water-heat interaction that produces phreatomagmatic eruptions at Taal, but at a smaller scale and without the involvement of new magma. They indicate a volcanic system in thermal flux, moving heat through a system that is not necessarily approaching major eruption, but is demonstrably more active than background. In Indonesia, Semeru volcano in East Java, the highest active volcano in Indonesia, has been in continuous eruption throughout 2026, producing small ash columns of 3 to 5 kilometers from its summit crater multiple times per week. This is within Semeru's baseline activity and is not by itself alarming, but it contributes to the regional picture. Multiple volcanic systems across the same arc region are simultaneously active at elevated states. In the Western Pacific, conditions at the surface of the ocean are themselves relevant. La Niña, the cooler Eastern Pacific phase of the El Niño Southern Oscillation, is currently active. La Niña drives above-average rainfall across the Philippines and Indonesia by intensifying the trade winds that push warm surface water toward the Western Pacific, enhancing tropical convection and producing anomalously wet conditions across the island arc regions. In Batangas province around Taal and in central Java around Merapi, rainfall totals this season have been above the long-term average. Increased rainfall in volcanic terrain has consequences that operate below the level of public visibility. On groundwater levels within volcanic edifices, the water that infiltrates through fractured rock and accumulates in the pore spaces of the volcanic structure rise with elevated rainfall. At volcanic systems like Taal, where the eruption mechanism depends fundamentally on water interacting with magma, a higher water table means more water available to produce phreatomagmatic explosions. The hydrostatic pressure in the system changes. The threshold for the kind of explosive water-magma interaction that drives Taal's eruption columns is not fixed. It varies with the amount of water available in the system, and La Niña has been increasing that availability. The evidence for a direct La Niña influence on Taal's eruption timing is limited. The statistical record shows some preference for Taal's major eruptions to cluster in wetter periods. Nay, but the sample size of major Taal eruptions in the instrumental record is too small to establish a robust statistical relationship. What the mechanism predicts, and what limited evidence supports, is a modestly elevated probability of phreatomagmatic activity at water-saturated systems during La Niña phases. Not a dramatic increase in risk, but a real one. The compound picture that emerges from the 60-day window is this: elevated microseismicity along the Philippine sea plate margin following a major earthquake. 2 Philippine volcanoes, Mayon and Canlaon, at elevated alert status. Continuous activity at Semeru. La Niña conditions increasing groundwater availability across the island arc region. And then, within a single 14-day window, the simultaneous acceleration of precursors at the 2 best monitored and most dangerous volcanoes in the region, culminating in two major eruptions within 5 hours of each other. No single element of this picture is, by itself, definitive. The Mariana earthquake might have no connection to the eruptions. La Niña might have had no influence on Taal's timing. Mayon and Canlaon might have been elevated independent of any regional trend. But the convergence of these signals within the same 60-day window is anomalous by any historical baseline comparison. The scientists watching this data are not in the business of claiming certainty without evidence. They are in the business of tracking probabilities. And the probability that the Western Pacific Arc is currently in a period of elevated overall stress. Not the certainty, but the probability is higher today than it was 60 days ago. Now bring all of it down to the level of the people living beneath these eruptions. Taal Volcano sits at the center of a lake that is itself surrounded by communities whose residents have, in many cases, lived within sight of the volcano for generations. The 14-kilometer mandatory evacuation radius now in effect covers approximately 380,000 people in Batangas province. In the municipality of Talisay, residents along the lakeshore face direct exposure to ashfall and the possibility of pyroclastic base surges, fast-moving ground-level ash clouds that can travel across the lake surface from the erupting island. In Laurel, Agoncillo, and San Nicolas, communities that depend on fishing in Lake Taal have been told to leave. Experience from the 2020 Taal eruption, which forced the evacuation of more than 376,000 people, showed that approximately 15 to 20% of residents within the mandatory evacuation zone did not immediately comply with evacuation orders. Some had nowhere to go. Some did not believe the eruption would reach them. Some returned to their homes to retrieve animals and property. The 2020 eruption remained at VEI 3 and did not escalate to the level that would have placed these non-compliant residents in direct mortal danger. The current eruption has not yet established whether it will remain at this level or escalate. If the alert at Taal rises to level 5, a designation that indicates a major eruption is occurring with potential for caldera-scale involvement, the evacuation radius expands and the total population under mandatory evacuation could exceed 700,000 people. The logistics of moving 700,000 people away from a volcanic caldera in Batangas province while simultaneously managing the ashfall impact on Metro Manila 70 kilometers to the north, a city of 14 million people, would strain every component of the Philippine emergency management system. Metro Manila is not under evacuation order. It is under an ashfall advisory. The distinction is important but does not mean Manila is unaffected. Fine volcanic ash from Taal is being carried by upper-level winds toward the northeast, toward the metropolitan area. Volcanic ash at sub-10 micron particle size, the particle range that the phreatomagmatic fragmentation at Taal produces in abundance, is a significant respiratory hazard. PM 2.5 volcanic particles carry adsorbed sulfur compounds, fluoride, and trace metals that are chemically reactive in lung tissue. They are not simply fine dust. They are fine dust with active chemical surfaces. The Metropolitan Manila Development Authority has issued mask advisories. The Department of Health has activated respiratory health protocols at public hospitals. Supermarkets and pharmacies across the metro area reported N95 mask supplies depleted within hours of the ashfall advisory being issued. Manila's water infrastructure faces a secondary risk. 2 surface water intake facilities operated by the Metropolitan Waterworks and Sewerage System draw from surface water systems in the Batangas region. Ashfall containing sulfuric acid compounds and fine silicate particles reaching those watersheds can contaminate surface water and potentially affect water quality at intake points. The MWSS has issued precautionary advisories and is monitoring water chemistry at those intakes continuously. The risk is manageable under current conditions, but it is real and it is being actively tracked. The agricultural impact on Batangas province is immediate and severe. The province is one of the Philippines' primary growing regions for Liberica coffee, known locally as Kapeng Barako, a variety found in few other places in the world, as well as coconuts and onions. The ashfall reaching agricultural land within 30 kilometers of the eruption is acidic, carrying sulfur compounds that lower soil pH and can damage both established crops and soil microbiological communities that support future growing seasons. If farmers who have not been evacuated are watching their fields receive deposits of material that will require clearing and remediation before the next planting cycle. Around Merapi, the geometry of the hazard is different, but the human stakes are equally specific. The 10-kilometre hazard zone around Merapi's summit contains approximately 300,000 people. The village communities along the Kali-Gendal River drainage on the mountain's southern flank, the drainage that the current pyroclastic flows have travelled down, have been the subject of mandatory evacuation orders. Some communities in this drainage are within the current 7-kilometre flow extent. Whether all residents complied before the flows arrived is not yet fully documented. 30 kilometres to the south, Yogyakarta is a city of 400,000 people and one of Indonesia's most significant cultural and educational centres. It is the site of the Kraton, the palace of the Sultans of Yogyakarta. It is home to multiple universities, including Gadjah Mada University, one of Indonesia's largest. It is a major tourism destination with the Prambanan Temple Complex, a cluster of 9th century Hindu temples and a UNESCO World Heritage Site, located at the city's eastern edge and within the current ashfall zone. Yogyakarta's Adi Sucipto Airport is closed. Road transport in and out of the city is disrupted by ashfall on road surfaces. The city is experiencing the same respiratory health challenges as Manila, fine ash accumulating on surfaces, in water supply systems, in the air. The compound emergency management reality is this: 2 national disaster management systems, the Philippines' NDRRMC and Indonesia's BNPB, are simultaneously managing major volcanic crises for the first time in the modern era of each agency's existence. Each system was designed for single-event national response. The protocols, resources, logistics chains, and command structures of both systems are fully committed to their respective crises. There is no established bilateral coordination mechanism between the Philippines and Indonesia for concurrent volcanic emergencies. The challenges that cross both national systems simultaneously, the integrated ash plume tracking, the combined atmospheric SO2 modelling, the aviation routing, fall into the institutional gap between 2 national architectures that were not built for concurrent activation. International humanitarian coordination through the UN Office for the Coordination of Humanitarian Affairs has been initiated, but OCHA's regional capacity for simultaneous volcanic emergencies across 2 countries in different administrative regions is finite, and the initial coordination is still in its early stages. The questions that the scientific community is most urgently trying to answer in the hours and days since both eruptions began are the questions whose answers are most incomplete and most consequential. The first is the question of connection. The detailed precursor analysis is underway at PHIVOLCS and PVMBG, as comparing the acceleration timelines at both systems against the seismic record of the past 60 days. The modelling of stress propagation from the Mariana Trench earthquake through the specific geometry of the Eurasian plate in this region is being conducted by at least 3 independent research groups with access to the relevant seismological data. None of this analysis will be complete in days. It may not be complete in months. The conclusion, when it comes, will either reinforce the standard independent event model, the coincidence interpretation, or provide the first robust evidence base for revising how volcanic hazard is assessed following major seismic events in arc settings. The implications of the second outcome are large enough that the analysis is receiving attention from volcanic hazard assessment programs globally, not just in the Philippines and Indonesia. The second question is specific to Taal and is being watched with particular care. The seismic events recorded at Taal in the 36 hours before and since eruption onset are not all originating from shallow depths beneath Volcano Island. Some are occurring at depths between 5 and 15 kilometers below the surface that correspond to the broader caldera system beneath the lake, rather than only the immediate volcanic vent. Taal's caldera is an ancient structure of approximately 234 square kilometers, the remnant of a series of caldera-forming eruptions in the geological past. Some of Taal's most violent historical eruptions, including the 1754 event, involved the caldera system itself rather than only the central island vent, and if the deep seismicity currently being recorded at Taal is indicating involvement of the broader caldera system rather than only the Volcano Island conduit, the range of possible eruption scenarios expands substantially. The maximum eruption size considered within the hazard assessment zone grows. The evacuation radius may need to expand. FIVOLC scientists have been publicly explicit about this possibility, while also being explicit that it remains unconfirmed. The monitoring data does not currently establish caldera system involvement. It does not exclude it. The difference between those two states is the difference between a major volcanic eruption and a potentially catastrophic one, and scientists are watching the deep seismic record with that understanding in place. The third question is atmospheric. Both eruptions are actively injecting sulfur dioxide into the atmosphere. The combined SO2 emission rate from both volcanoes at current levels, if sustained over the next 72 hours, represents a total atmospheric sulfur loading that atmospheric chemistry teams are modelling with urgency. The relevance of this modelling is not primarily regional air quality, though that is a real concern for communities in both the Philippines and Indonesia. The relevance is potential stratospheric forcing. For volcanic SO2 to affect global climate, it must reach the stratosphere in sufficient quantities to form a stratospheric aerosol layer that persists over timescales of months to years. The 1991 Pinatubo eruption injected approximately 20 million tons of SO2 directly into the stratosphere in a single VEI-6 event, and the resulting aerosol layer reduced global average temperatures by approximately 0.5 degrees Celsius over the following 2 years. The current eruptions are at VEI 3 to 4 scale, substantially less energetic than Pinatubo. A single eruption event at this scale would not be expected to produce climate forcing at Pinatubo's level, but both eruptions are ongoing, not single pulse events, and if either escalates, if Taal's deep seismicity indicates caldera involvement and the eruption intensity increases, or if Merope's dome collapse is followed by continued high-intensity explosive activity rather than a return to dome building, the cumulative SO2 injection into the stratosphere over days and weeks of sustained activity could become climatically significant. Additionally, the combined loading from two simultaneous eruptions, now even at VEI 3 to 4 scale each, produces a different atmospheric chemistry scenario than either volcano individually. The models are running, the results are preliminary. The possibility is being tracked. The history of the region that these two volcanoes call home contains the answer to what the Earth looks like when the Western Pacific Arc enters a period of elevated simultaneous activity. That history is not the history of isolated dramatic events. It is the history of periods, extended windows of time during which the arc system as a whole burns at a higher rate than its background. In the decades before 1815, the geological and historical record indicates that the Indonesian arc system had been in a period of broadly elevated volcanic activity. Multiple volcanoes were active simultaneously in the years and decades leading up to Tambora. The Great Eruption of 1815 was not an isolated anomaly emerging from a quiet system. It was the most extreme expression of a system that had been building toward elevated activity for years. Whether Tambora's eruption was in some sense the culmination of a system-wide period of stress, or whether it was simply the largest event in a period that would have included large events regardless, has never been definitively answered. The 1994 coincidence of Rabaul and Merapi, the last event directly comparable to what happened in the past 24 hours, was followed by a documented period of elevated volcanic activity along the Western Pacific Arc. The Smithsonian Institution's Global Volcanism Program maintains comprehensive records of volcanic events worldwide since 1968. Its database shows that the 5-year period from 1994 to 1999 included a statistically elevated rate of significant eruptions along the Western Pacific Arc relative to the preceding 2 decades. The elevated period was real in the data. Whether it was caused by the 1994 dual eruption event, or whether the 1994 event and the subsequent elevated period were both expressions of the same underlying geological state, is not established. What the historical record shows, across multiple time periods, is that the Ring of Fire's western arc does not operate at a constant rate. It has states. There are periods of relative quiet and periods of relative activity. Those periods are not random noise. They have durations of months to years. They affect multiple systems across the arc simultaneously, and they are distinguishable in the geological and monitoring records. The precursor signatures of the current period, the 60-day seismic background, the 3 elevated alert volcanoes, the dual eruption event, match the opening signatures of previous elevated activity periods in the record. This is not a prediction. Volcano science does not predict in the way that the word implies certainty. It describes probabilities and precursors and pattern matches. The pattern match between the current situation and the opening signatures of previous elevated activity periods does not establish that the next months will see additional major eruptions along this arc. It establishes that the probability of additional significant volcanic events in this region is currently higher than it would be during a quiet baseline period. It establishes that scientists with access to the same data you now know about are watching more closely and more broadly than they would be if this week had produced only one eruption. The Ring of Fire does not send press releases. It sends signals. The signals from the past 60 days are anomalous. 2 volcanoes have already responded to them. 125 others have not yet. And that is where the question lives that this week's events have placed on the table and that cannot be answered with the data currently available. The Ring of Fire's western arc contains 127 historically active volcanoes. Taal and Merapi are among the most intensively monitored. They have dense seismic networks. They have gas monitoring systems. They have GPS deformation sensors. They have dedicated scientific teams with decades of institutional knowledge about each volcano's specific behavior. They have community-based evacuation programs. They have international scientific collaboration and decades of published research on their eruptive histories. The eruptions happening right now were anticipated in the sense that both volcanoes were known to be active and capable. The monitoring systems did their jobs. the precursors were read correctly. Evacuations were ordered before the eruptions peaked. Most of the other 125 volcanoes on this arc do not have this infrastructure. Volcanic monitoring across Southeast Asia and the Western Pacific varies enormously. Some volcanoes have a single seismometer operated by an understaffed regional office. Some have no instrumental monitoring at all. Some have historical eruption records that extend back only a few decades because the institutions to document eruptions did not exist before the 20th century. Some of these volcanoes sit above or near populations that have no established evacuation procedures, no warning system, no institutional memory of how a previous major eruption unfolded because it unfolded before living memory. If the geological state of the Western Pacific Arc is genuinely elevated, if what has happened in the past 60 days reflects a real change in the system's behavior rather than a coincidence of independent variables, then the question is not only what happens next at Taal and Merope. The question is what is happening right now at the 125 volcanoes that are not Taal and Merope. Which ones are showing the same precursor acceleration that Taal and Merope showed 14 days before they erupted, but through monitoring networks too sparse to detect it, analysed by agencies too understaffed to act on it in time, in communities too isolated or too resource-constrained to evacuate effectively even if the warning came. The 5-hour and 12-minute gap, understood fully, is not just the gap between two eruptions. It is the gap between what the best monitored volcanoes in the region can tell us about the geological state of the system and what the rest of the arc's volcanic record is doing right now in the absence of adequate monitoring. It is the gap between what happened at Taal and Merope, which was anticipated, prepared for, and is being managed, and what could be approaching at unnamed systems with one seismometer and no evacuation protocol. 5 hours and 12 minutes. That was the window. And the window was not, by any measure of geological significance, a long one. Merope did not give Taal's monitoring teams days or weeks of separate warning. It erupted while the first evacuation convoys were still moving away from the lake shore. While the ash column from the Philippines was still climbing, the dome in Indonesia was already falling. The geological system that produced both events did not sequence them conveniently. It compressed them. The scientists who were awake through the night, tracking both eruptions simultaneously, the teams at PHIVOLCS and PVMBG communicating across the 3,200 kilometers between Manila and Bandung while managing crises in their own backyards, were asked to answer two questions at once that their instruments, their protocols, and their institutional architectures had each been built to answer one at a time. The aviation safety system was asked to track two plumes with two models and produce one picture for pilots who needed one picture. It could not. The atmospheric chemistry teams were asked to model the combined SO2, loading from two simultaneous eruptions, and produce a single answer about potential climate forcing. That answer is not yet available. The bilateral emergency management coordination that 700,000 evacuees in the Philippines and 300,000 in Indonesia simultaneously needed did not have an existing framework to operate within, because no one built one. What this week has demonstrated, with the specificity of documented real events and specific gaps in specific systems, is that the global architecture for managing volcanic hazard was built for a world where major eruptions are rare, independent, and widely spaced in time. When the geological system produces events that are simultaneous, overlapping, and compound, as it apparently can and does, the architecture shows its seams. The Earth is still moving beneath both eruptions. The precursor monitoring at Mayon and Canlaon and Semeru and the 120-odd other systems along this arc continues to run, are recording signals that may or may not represent anything beyond normal background activity. Signals that may or may not be building towards something that will be obvious in retrospect and ambiguous right up until it isn't. Scientists don't have the answer yet. They are watching. The instruments are running. The analysis is ongoing. But the question that 5 hours and 12 minutes placed on the table is a real one, grounded in real data, pointing toward a real possibility that the geological record says has happened before and the monitoring record says cannot be ruled out now. The Earth does not always give warning in the way we build our systems to receive it. Sometimes it speaks in compression, in coincidence, in 5 hours and 12 minutes. Whether that compression is the whole story, or whether it is the beginning of one, that is what the instruments are trying to determine. And the answer, whatever it turns out to be, will matter far beyond the two volcanoes that have already spoken.